All right, ladies and gentlemen, let's talk a little bit about our graphing in physics. We did a little bit of this with one of our worksheets in class, but I want to go over it real quickly with you. Now, in order for you to have great graphs, it has to have certain things. You have to identify the independent and dependent variables. You need to choose your scale and show that scale so that it fills up at least 2/3 of your graph. You need to plot the independent variable on the x-axis and the dependent on the y-axis. If you remember, there's the acronym mix and dry or dry mix, and that would be your dependent or responding variable goes in the y-axis for dry, and then your manipulated or independent variable goes on the x, which would be your mix. You need to make sure that you label each axis with not only the name but also the unit. You need to title your graph. And then if the data points appear to be in a line, you should draw that best fit line with a ruler and a sharp pencil. So we use graphs to examine experimental data, okay? And the thing to remember is that with this particular information, we said as weight or a force is added to a spring, it will stretch. So this is the data we got. We should then graph it. And to have a great graph, we identify the independent variable as our force, because we changed to the force, is what we chose to change. And then we measured what happened to the spring, how much it stretched. So that was the dependent variable. We are going to choose that every 1 unit or square is going to be 5 centimeters. We're going to plot the independent on the x and the dependent on the y. So it should look something like this. So we have our data points plotted, we have our labels with our units, we have our scale that's taking it up, and we have our title. We're good to go. Now, if the data appears in a rough line, we did that line, we titled it, we labeled each axis part. Like I said, good to go. So what kind of relationship does this actually represent? That actually starts to tell us important things. And in graphing, for AP, there's 2 things that you're always going to use your graphs to figure out, and that is slope and area under the curve. So this relationship, though, we can automatically say as one goes up, the other goes up. So we would call it a direct relationship or a linear relationship. Okay, so we're going to talk about the different types of relationships that we can see in our physics graphs. And there's 3 that typically occur in physics. The first one would be a directly proportional graph, and it would create a straight line. If we think about the formula for a line, when it is directly proportional, it would be y equals kx, where k is a constant, or that would be our m value. So that would be our slope value, would be that k. So this would be, so the formula for a line was our y equals mx plus b, so this would be our y equals kx plus b, but b here is 0, 0. So that would be for graph A here. It's a directly proportional, and that would be our line for it. Now, if it varies inversely, okay, it could be a hyperbola instead, which would decrease this way. So we could say y equals our k times 1 over x. Okay, so this would be our curve. And then we could also say that it varies directly with the square, which means it starts at 0, but it increases, and this would create a parabola. And our line formula for this would be y equals kx squared. Now for graph B and graph C, we are going to not deal with curves and finding the area of, or excuse me, the slope of a curve. That's calculus-based physics, and that would be taking derivatives and some things like that. So instead, what we will do is we will learn to linearize the graph so that we can work with it as a straight line. Okay? And so those are the three types of relationships. Now, we talked about some vocabulary words in class, and that would be reading from a graph between the points would be interpolation, and reading from the graph beyond the point, the experimental data, would be extrapolation. So if we read in between this -20 and this 270-ish, then we would be interpolating. But if we read something that was over here in 40, that would be extrapolating. Or if we read something that was over here in -180, that would be extrapolating. Let me move my little thing around. So suppose you record the following data during a study of relationship of force and acceleration. I want you to prepare a graph. So the first thing is, which one's the independent, which one's the dependent. Okay, we're choosing to change the force. We're then going to measure the acceleration. And then we would label. So force goes on the X, acceleration goes on the Y. Force was measured in newtons. Acceleration was measured in meters per second squared. We have a title, we have a scale, and we graphed. So describe the relationship. We would describe that as directly proportional, and you always say that the Y is somehow related to the X. So the Y was acceleration, and it's directly proportional to the force. So what's the slope of this graph? Well, if you remember, slope is the change in Y over the change in X. So we could take our data, and we could say 25 minus 0 over 40 minus 0, and we would end up with 0.625 divided by 1. Now, if we keep the units there, notice that we have meters per second squared on the top, and we have for force is newtons, and newtons are made up of a kilogram meter per second squared. You don't know that yet, but you will know that, so that's why I'm telling it to you now. Okay? That's something we'll work on when we're learning about forces and that particular unit. But you'll notice that meters per second squared is on both the top and the bottom, so we end up with 0.631 over a kilogram as our units, or kilograms to the -1. So if I ask you what does this physically represent, you need to look at what the units stand for. So this particular one, this would be the inverse of the mass, because kilogram is our mass unit, and since it's 1 over a kilogram, it's the inverse of our mass. That's what the slope tells us. Okay? So write an equation for the line. Well, our basic line equation is y equals mx plus b. Then we could say y was acceleration, and x was force. And our b value was 0 because it went through the 0, 0 mark on our graph. Okay? Our k value actually was our 0.63. So we could actually have even rewritten this as a equals 0.63 kilograms to the -1 multiplied by our force plus 0. That would be another way of writing it. So I could use this line formula now to actually make predictions. I could say, what's the value of the F if I said the acceleration was 15 meters per second squared? Well, if I didn't want to do it on my graph, I could do it with the line equation now. Either one would work. So I could plug that in, solve for force, and end up with 24 newtons. Okay. Then I could also ask for acceleration and say if I plugged in 50 newtons into that line equation, now I could say it was 0.63 times 50 equals 32 meters per second. Now, I will tell you a couple of things. Some of these examples I'm showing you, like right here and right here, I didn't include the units. I do expect you to include the units when you do your work, which is going to be something that you guys will probably bug me about, but it's going to be really important that you hold on to those units the whole time while you're going through problems, okay? So this particular part of this PowerPoint is now actually linearizing. And so we can talk about what it would look like as a graph and what it would look like as a, if you had to linearize it, what would you would do and what proportionality it is. That's the word I was looking for. So if we look at this data right here, it kind of looks like as one goes up, the other goes up as well. Okay, so if we graph the data, so we probably predict that this is going to be directly proportional. So if we graph the data, we could say that the velocity is directly proportional to the time. To graph the data, it looks like a line. So that's pretty correct. Now, these graphs aren't great graphs because they're not labeling the units and name of the label and the units for each axis, but they're pretty good. Okay, so we could draw a best fit line and we could find a slope. This one, on the other hand, looks a little different. So I will tell you, just looking at it to predict what relationship it is really hard for me. I really do struggle with that. This one's going up as this one goes up. So I know it's going to be either directly linear or directly with some sort of square or something. So I could look at it that way, but I will tell you after I figure out that it's directly or indirectly, beyond that, I typically have to graph it to figure out the proportionality that I'm going to predict. But because I only picked 3 earlier that I showed you, I said it was directly linear, I said it was direct with the square, or I said it was inversely. Okay, so this one I will say probably, since I only showed you 3 and I'm showing you examples, is directly with the square. So the position, the y, is directly proportional to the time squared. So it is always that x value that we're talking about is that squared. So when I graph the data, it looks like a curve. I don't really want to look at the data as a curve, though. I will be teaching you what that curve means, but I won't ask you to find the slope of it. So if I wanted you to find the slope of this, I would actually want you to linearize the data. And to do that, we're going to have to get rid of this squared. So what we do is we take this x value for time, and we square all the x data points. We'll now create a new x data column. Okay, so these will all be time squared. Once we do time squared, we'll go ahead and put that on the x-axis. And so this would be written this way. That's what this would look like. But if I wanted to linearize it, I could now make it look like this. So if I said that x squared value, notice I took that parabola and changed it to a line. And finding the line or slope of this would be really easy. Also, then I could look at what the units of this slope would be, and that would tell me something also. And we will get to what that means later on. I will give you some more tidbits about it, okay? Because meters per second squared means something to us. Meters per second means something to us. So we'll talk about all of that in class. This one, what's the relationship? Well, as we go up in this column, it goes down in this column. So I'd probably say we have an inverse relationship here. So that would be our volume is inversely proportional to our pressure inverse. So it actually looks like this. It's our hyperbola when we graph it. Again, to go ahead and linearize it, I'm going to take my x information and I'm going to do the inverse of it and create a new column of x information. When I do that, I'm going to regraph this. Oops, I didn't want to do that. I'm going to regraph this data in this inverse column on my x-axis and plot the v information as is. So it will linearize it and make it a lot easier as my to find my slope. So then we would actually have meters cubed over our pressure. So that would make a big difference. So in our slope. So that ends this one. Sorry, it was a little more than 10 minutes, but again, we will talk about linearizing in class also. Okay? Have a good one.